All right, welcome everybody to round two of the Introduction to Rust streams that I am putting on. The goal for today is really to continue on from last time. So if you haven't checked it out before, make sure to check out my previous stream, the Introduction to Rust Part 1, and I'll be talking about where you can find that in just a second. We're really going to continue on from last time, have a bunch of fun, ask a bunch of questions, and try and take it slow and see how much about Rust we can learn today through the session. So without further ado, I'm going to pop on over to my browser here. What I went ahead and did is put the code up from the last stream on to GitHub here, so you can find it at Llvm Intro to Rust Streams. On my GitHub page here, and I've got a little bit of a README for you on how to get started, and you can see where we were with the code last time. So if you don't have the code handy, you can go ahead and just clone this real quick, and you have the code ready to go. This is kind of where we left off from the last stream, and that's where we're going to get started from. This is the second stream of this series, and so if you haven't seen the first one, this may be a little bit more confusing than it should be. Maybe it's best to just take a pause, go watch the first stream, and then come back and watch this afterwards. It will be up on YouTube if you're watching live. If you're already watching this on YouTube, hello in the future. I hope it's doing well. But if you want to find the first part, you can find it here on YouTube page, where you can learn all you want about Rust through part 1 here. This is on my YouTube channel as well, where you can find a whole bunch of other streams as well about Rust and about computing. Usually they're a bit more of the intermediate level in Rust, or advanced beginner at least. So go ahead and watch this stream, and then you can check out the other videos afterwards and learn some more about Rust. All right. So we did have a quick question that I wanted to get to before we get started. Somebody in chat was asking, should I really start a career in Rust? And this is an interesting question because it always comes down to, like, I'm beginning out in programming. What language should I pick? Kind of all these things. And I think that Rust is a really great choice. Nowadays, it's gaining popularity. Certainly, you'll learn a lot about computer science, about programming. There's a lot of great concepts that can transfer to other languages and things like that. But the reality is that, if your sole goal is to get a job, then Rust is probably not the language as of right now to choose, just because there are a lot more jobs in other languages. Now that may change in the future. There seems to be a very bright future for this language, but it's new, right? When you're comparing it with something like C++, which has been around since the early 80s, late 70s even. Or Java, 95, Python, early 90s, and it doesn't have kind of like a killer use case in terms of like a company saying this is, if you want to do X, you must use Rust, like you have with Swift. If you want to write iOS applications, sure, you could use Objective-C, but like even Apple's like, no, come on, use Swift, right? And there's not that with Rust. The use case for Rust is a little bit more nuanced. So with all that said, like, don't start a career in computing or in programming or whatever based on a language. Pick a use case, learn the language that's good for that use case, and then learn another language. In my career, I've shipped production software, and I think it's probably around 10 languages or something like that. And so, I like Rust a lot. I do Rust basically every day at work, but I can't imagine that Rust will be the last language that I'll use in my career. So hopefully that helps a little bit. Now, for those with more established careers, welcome. We'll be switching over to a new language today, and that language is Rust. And let me know if anybody needs any help getting started. In the last stream, we went through how to install Rust and getting your programming environment set up. I'm going to assume that you've already done that because this is part 2. And that would put you over here in, get rid of my little practice session there. That will put you in this state right here where you have the code looking like this. And hopefully you've cloned down the repository and you have your code set up to look like this. So let me know if you have any questions about that. But then we'll get started with a review of what we did last time for a couple of minutes, just to kind of remember where we were. So last time we started creating a key value database that allowed us to store keys and values inside of a very simple database, which was just a file on disk where our keys were separated from our values by a tab character, and each key value pair, of which we could only ever have one because of a bug in our program, they would be separated by new lines. And so what does our program actually do? Well, it's quite simple. For now, what it does is it calls standard env args to get the arguments from that are passed in from the command line. It then calls skip to skip the first one of those, because the first command line argument on Windows and on Linux is going to be a path to the executable binary itself, which we don't care about. And then what we do is we call arguments.next. Now remember, .next is a way to advance the iterator one and get the next item in the iterator, which of course args, or to be more precise, skip args here, is an iterator. And so we call next to get the next item, which presumably, which we're saying is the next argument in our arguments list is going to be the key. Now we have to call expect here on our arguments. Why? Because arguments.next returns an optional string. The reason for that is maybe we didn't pass any arguments, right? Maybe we didn't pass any arguments at all, and calling arguments.next should return what? Well, if the argument is there, it will return a string, and if the argument is not there, in a lot of other languages, it would return null, but in Rust, there is no null, so really what we're getting back from next is an optional string. It tells us whether the string is there or whether it's not. And what .expect does is say, hey, if it's not there, crash the program. And we do the same thing with value using unwrap instead of expect. Expect just lets you customize the message that gets printed to the screen. It's basically the exact same as unwrap. And then we print out something to the screen. The key is the key and the value is the value here. And then we format a string using this format macro that allows us to put our key and value into a string in a certain format. And that format is the key, the tab character, the value, and then the new line character. And then we call standard fsWrite to write the contents to a file called kv.db. And then at the end of all that, what we did was we started abstracting this idea away because we found we had a bug, right? What we were doing is every time we would run the program, we would get the key and the value from the command line arguments, and we would store them into our database, overwriting the previous values, which is not a very useful database, right? You want to be able to like keep all the values in the database and not continually overwrite them every time you write a new value. So in order to abstract away, we created a database type, a database struct. And that database struct had inside of it one field, a field called map, which was a hash map. A hash map, more precisely, of strings to strings, so string keys and string values. And the reason we picked hash map is because we're building a database, a key value database, and hash maps are data structures that kind of mirror that, right? Hash maps, also known as dictionaries, or in JavaScript, objects, are key value data structures. So it's a great way to model our database. And we learned that you could do impl database to add associated functions to that type. And we only had one associated function so far, called new. And we learned new is nothing special. It's just a function we called new, and that's out of convention more than anything. There's nothing special about the name new. We picked new because it's going to create our database, and new is the conventional name for such functions in Rust. And it's very simple. It returns back to us a result of a database and standard IO error. And we learned that results are types that model things that could either be successful, and if they're successful, they're the OK variant, result OK. And if they're an error, then you get back result error, ERR, result error. And so by looking at the signature, we could already tell, okay, we got a result, and if it's successful, we get a database back, and if it's an error, we'll get back a standard IO error, which is just an error type from the standard library that has to do with IO errors or input-output errors. And we kind of do something similar to before. We read from the string. We read to a string from kb.db, so this looks at kb.db on our file system, the file at kb.db, and reads the contents of the file as a string. Now we also learned this question mark thing is basically saying read to string, that function returns a result. And what we want to do is if it is okay, if it's result okay, then put the value into our contents variable right here. And if it's an error, just pop it on up. And this is a great way in Rust to simply say, I want the caller of the function to deal with the error. I don't want to deal with the error myself. And so contents is just a string, a whole string that represents the file, and we call contents.lines, which is a method on string, which gives you an iterator over the lines of that string. And we iterate it using for in. So for each line in contents.lines is how you can read this. And that gives us a line inside of the contents string. And we split that line on tab characters, saying we want to split into two chunks, basically, using split n, which is another method on strings, which allows you to get basically chunks of a string split on a pattern, in this case the tab character. And chunks is itself an iterator, so we can use the same iterator functions that we used above, like next, to get the key and the value. And we use expect here to crash the program if there is no key, and to crash the program if there is no value. And then in our map, we call insert on it, which allows us to insert the key and the value into the map. And then we return database with OK, saying everything was good. And the last thing that we learned about is contents here is a string, capital S string, string string. And what we learned what that meant is that contents is an owned string. It owns the data that is associated with it. And what ownership means is that when contents goes out of scope here at the end, the value will be dropped. And dropping a value in Rust means freeing up any associated resources with it. And what associated resources do strings have? They have heap allocated data. Our string is allocated on the heap. Now, if you're not familiar with the stack versus the heap, this is something that you should read about on the side. But basically, the heap is just our kind of dynamic memory, the place where we can say, hey, I need some more memory, give me some more memory. And we ask a memory allocator to give us more memory, and it gives us more memory on the heap. And when we're done with that memory, we need to be able to say, okay, we don't need that memory anymore. Now, in other languages, with garbage collection, the garbage collector does that for us. It determines when things are no longer needed and then throws them, collects them away and frees that memory when we're done. That's what's great about garbage collection. We don't have to worry about it. And in other languages like C and C++, which use manual memory management, we are in charge of doing that. So when we need memory, we call malloc. And when we need that memory, when we want to give that memory back, we call free. Rust allows us to have kind of the best of both worlds. We don't need to explicitly free our memory. The language kind of does it for us at compile time. And so contents here, when it goes out of scope at the end here, will free its memory. And then we learned that line here is not a string, capital S string, it's an ampersand stir, also known as a string slice. And what that is basically a pointer, or like a window essentially, that lets you view parts of the string. And so when we have line here, we're actually seeing the memory of contents here. We're seeing the first line in memory of contents. And so when line goes out of scope, it doesn't matter. It doesn't own the value. It's a reference. It's borrowing that value. And so when line goes out of scope, we don't free any memory. It's simply just borrowing that value and taking a peek at it. But it's contents that's in charge of deciding when the string will be freed. And we can see this down here as well with key and value. Key and value are ampersand strings as well, because they are literally pointing up into the content string and saying, okay, and really if you want to see what an ampersand stir is in memory, it's a pointer, so a memory address, and a length. And it says at that memory address is the key, and it's how many bytes long. And that's what we see. And same with value. It's just pointing up into the content string and saying, hey, over there, that's where you're going to find the value. But our map here expects capital S strings, own strings. It wants to hold on to the data. It wants to own that data. It wants to decide when that data will be freed. And so what we have to do is call toOwned on our key and our value to turn our key and a value from string slices, from ampersand stirs, into capital S owned strings. And toOwned will take the data that's at key and value and copy it and create a new string object that owns a copied piece of data that is exactly mirrors what key and value were. All right, so that's kind of a review of where we are. Especially that last part may not make 100% sense yet, but that's fine. This is kind of like the essence of Rust here. So I'm going to go to chat real quick to see if there are any questions, and then we can kind of go on from here and figure out what this all means, what this does to our program. So why did a borrow reference to string end up as ampersand stir and not... Okay. So the question is, why is it ampersand stir and not ampersand capital S string? Why is this returning us this weird ampersand str type instead of like an ampersand capital S string? And these are two different concepts that really kind of have to drive you home. And I'm going to try to talk about it in terms of actual memory, because I think that helps. If you're not used to thinking about computer memory, maybe you're coming from a high level language where you don't really have to think about this stuff, stick with me and we'll get through this together. What is this content string actually? Like, what is it in memory? What the contents string, capital S string, is a struct, just like our database struct, composed of three different things. It is composed of a pointer to the data on the heap. So it's pointing up to the heap, to a memory address somewhere where the data of our string lives. And so somewhere in memory, there's the contents of our file, and it has a memory address saying, hey, that's where you're going to find it. The second thing it has is a length. And that length is going to be however long our string actually is. So if it's 12 bytes long, length will be string. And the third thing that it is a capacity. And this is how much room on the heap has actually been allocated for this string. Now you might be confused. What's the difference between length and capacity? Length is literally how long is this string. If the string is hello world, it's going to be however long, how many bytes hello world is, 10 or 12 or whatever. I'm not going to count hello world right now. But capacity is like, maybe we allocated a gigabyte of memory on the heap just to be careful. Like, hey, we want to reserve a whole bunch of memory. Then the capacity will be a very large number, right? It will be a gigabytes, however big a gigabyte is in terms of a number. I forget. And so capacity represents the actual the amount of space on the heap that we have reserved for our string should it want to get bigger. Ampersand stir, on the other hand, is simply just the pointer to the data and a length. Now, why is that? Why does capital S string get this capacity? What does that mean? That's because capital S string is growable. We can grow the string bigger. We can say, hey, the length is now 12, but we've reserved, a megabyte of space on the heap. We want to add an extra couple of characters to our string. We can go ahead and do that. And string knows how to do that. And, when we're done using the string, it will free itself. But with ampersand stir, what it is simply just a view into a string. It's not growable. It's really just a static thing saying this is where the data is and this is how long it is. There's no way to grow it. So going back to the original question, what is the difference between an ampersand string and an ampersand stir? Ampersand string is simply borrowing that struct of three things. So it's borrowing the owned struct. And what that means is you're going to get the whole string there. It's all the data. It's the capacity. You can read it. You can't modify it. We'll see why that is in a minute. An ampersand stir, on the other hand, is a view into some larger string data. So, for instance, line here is simply each line as we go through. Whereas if we were to get an ampersand string, it would have to be a reference to a pointer to a reference to the entire string. Hopefully that makes a little sense. And we'll strings, I struggled whether to start with strings as the first thing because they're kind of the weirdest of all the things because there's the difference between string slices and borrowed strings and owned strings and stuff like that. Hopefully this will become clearer as we keep going. And there was a question of, does this imply the existence of str without the ampersand? So just a bare stir? Yes, but for reasons that we won't get into quite yet, you can never really have just a plain str type. And we'll see why that is. Maybe not today, but in a future episode. All right. Any more questions about this? If you're still kind of like fuzzy on the idea of ownership and borrowing and what that all means, like, don't worry, that's actually what we're going to dive into now a lot more and talk about this concept of ownership and borrowing with our database type and how we can borrow and ultimately drop and free the memory that our database holds on to. This is a particular example where Rust is, at the end of the day, a systems level language. We have to worry about every single kind of allocation of memory that we're doing because we're a systems language. We need to care about those things. If you say, I don't care if my language allocates for me without me knowing about it, that's wonderful. It's fantastic. Maybe Rust is not right for your use case then. And that's why, as when you become an experienced Rust developer, it becomes important to know things like to own. Okay, that takes a ampersand stir, a string slice, and turns it into an owned string. That must mean it allocates new data. And so it's very easy to tell for a Rust programmer exactly where your program is allocating and, importantly, deallocating memory. All right. So it's time to write some new code now. And chat, don't worry. If you have more questions about the code that's already existing, keep them coming. I'm totally happy to go back and answer more about them. But we're going to take a step forward and try and write some new code to fix the bug that we currently have, which is we're consistently overwriting our database over and over again. And that's because, we set up this database, right? But we're not actually doing anything with it, right? We've got database new, we call expect here. If there's an error, we'll crash, but we get a database, and Rust is even telling us this with this yellow squiggly line. It says unused variable database. We should be using this variable, and we're not using it. So let's go ahead and use it. What do we want to do? Well, our database is populated with the contents of the kv.db file. That's great, but when we're getting in a new key and value up here from our arguments, we should insert that new key and value into our database. So how can we go ahead and insert into our database? Well, currently there is no way, right? We have no capacity for inserting, but we can go ahead and add that by adding an insert method. And what it's going to look like is something like this: database.insert, and then we'll pass in key, and we'll pass in value. And as of right now, we're going to get an error saying, I don't know what insert is. There is no method insert on database, which is true. We have no method insert. So how do we add methods? Well, we know how to add associated functions here, and all that methods are functions that take the type itself as the first argument. And so what we can do is say, we have a function called insert. We know, for instance, that it's going to take a key and a value, key string and value string. And if we were to do like this is not a method, this is an associated function just like new, but that's not what we want. We want a method, and a method takes self as its first argument. This is the only thing that differentiates methods from functions, and in fact, methods are really just functions, just with some syntactic sugar. And we could, if we wanted to, instead of writing database insert key value, we can write database insert database key and value. This is also completely fine syntax, albeit in this case a little strange and not idiomatic, but really you can see that database.insert is just syntactic sugar for this right here. But we're going to go ahead and use the idiomatic way of doing things with the dot syntax. Okay, this is great. So we've got a method insert that we're calling with the key and the value that we got from the command line. And in fact, let's go ahead and we'll just get rid of our writing. We're no longer going to write to the database here. We don't need to format it as a string anymore. We can still print it out. That's totally fine. Now we're going to insert our key and our value into our database. And of course, this database exists in memory somewhere. It's the keys and the values are living inside of this hash map. So we're going to eventually need to add back the aspect where we're writing that to disk, but for a minute we won't get to that. And what are we doing here? Well, what we want to do is get the hash map from the hash map that we're storing, which we called map, this field right here, from our database, and call insert on it. And insert is just a function that comes with the hash map from the standard library. I use the term insert probably because I knew that the hash maps term was insert. You can use whatever names you want to use, but insert here is defined in the standard library on hash map. And we can pass in our key and our value. Now we're going to get an error message here, and we can hover over it and see what it says. Scroll down here, and it says mismatched types. We expected the unit type, but we found the enum option string. Well, what does that mean? And in fact, I think if we go ahead and run cargo check here, we'll get a better error message. So this is a tip to you who are using Rust Analyzer. If you see an error message that's a bit confusing, go ahead and run cargo check inside of your terminal, and you should end up probably with a little bit more helpful error message. And this indeed is a bit more helpful. It says it expected up here unit, this type, which is the default type. When you don't provide a return type from functions in Rust, it defaults to unit, which is essentially like void in other languages, because of the default return type. And it seems that .insert here is returning this option string. And we can look at the documentation for insert real quick in here and see what it says. So it says insert's a key value pair, and in fact we can see already here, right, that it returns an option v, so optionally gives back something of the type whatever the value type is, which is v here. If the map did not have this key present, none is returned. So essentially what it's doing is it's returning back the previous value that we already inserted in, which we don't care about, right? We talked about this last time. We don't care about that. So we can just add this semicolon here, and the semicolon says ignore the value that gets returned. And we still have an error message, and we should get used to that because we're going to get error messages from the compiler a lot in Rust. And it says cannot borrow self.map is mutable as self is not declared as mutable. So again, in Rust, everything is immutable by default. Self here is immutable, but we're trying to mutate it. We're trying to write into the map that self contains. And so we actually have to go ahead and declare it as being mutable like this. And now things should compile. Any questions about this? Does this make sense? Anything that was weird? Let me know and we can go over that. So this is working. We could go ahead and run it, but it's not going to do anything interesting, right? Because at the end of the day, we're not actually going to write any of this to disk. So like our kv.db file is not really being changed at all and anything like that. So we insert our key inner value in memory, and then the program ends, and all the memory is reclaimed and nothing really happens. There's a question here, why doesn't database have to be let mute? Right here. It doesn't have to be mute because, for a reason, let me wait just a second to describe that, because that's actually going to be somewhat answered by what we're going to talk about next. So hold on one second for that. All right. Now, what happens if we want to store the same value for the key that is provided when we uppercase the key? So essentially, when we're running, kv store, and we type hello and world as our key and our value, Chad is asking, why is self not a borrow yet? Bear with me a second, Chad. It will be. But I think it's important to see what happens when it's not a borrow. We haven't really talked a ton about borrows yet, so hold on one second. When we type in kv store, I want our database to not only store hello world with the key hello and the value world, but I also want it to store hello, all uppercased, with the value world, so that if we happen to want to look at the key by all uppercases, maybe that's part of our use case for this database for whatever reason, that we can also find world as well. Now there's many ways to do this, but I'm just going to do the simplest one here. I'm going to go ahead and store key and value, and I'm also going to insert key dot to uppercase here. And everything kind of breaks. Everything is breaking, and we'll see why in just a second. If we look, and in fact, I'm going to go ahead and instead of showing you in the inside of code, I want to go ahead and show it to you in the terminal because it's much clearer in the terminal. So cargo check. It's saying use of moved value database. The move occurs because database has type database, which does not implement copy. Okay, we don't know what copy is, but that's fine. database moved due to this method call. So essentially on line 10, when we called insert, apparently database moved into insert. Okay? We'll talk about what that means in just a second. And then we tried to use database again, which apparently we can't do. So what does this mean? This is the essence of moves, which is an essential part of the borrow checker, of borrowing and ownership in Rust. We declared self here as just being self. And what that means is when we call insert, the database that we're calling insert on will move into the insert function. And at the end of the insert function, self will be dropped. The memory that self contains will be freed. So again, why is that? That's the definition of ownership. Ownership, we can change ownership by moving things. Moving, you can think of moving as basically transferring ownership. This database variable owned the database memory. And then when we call database.insert, we moved this database memory into the insert function, and now self here owns that memory and is responsible for when it gets dropped. And so if we want to know when it gets dropped, we just have to ask ourselves two questions, essentially. Does self get moved anywhere? And nowhere in here does self get moved. And if it doesn't get moved, where does it go out of scope? It goes out of scope at line 33. So that's where self gets dropped. And when it gets dropped, self will free its memory. The memory that it drops its memory. It drops the hash map. Hash map, when it drops, it frees all the memory that is contained inside of it, including all those strings. So there's a bunch of memory that represents this hash map, and it will all be freed on line 33 when we drop self here. And essentially what we're getting here in this error message is just saying you moved database into insert, and then you try to use database after you've moved it. So you've transferred ownership over to self inside of this first call to insert, but then you try to use it. You can't transfer ownership of something. If I give you a book, I can't then continue to use the book because I've given it to you. And that's essentially what we're trying to do here. We're trying to give ownership over to this insert function, to the self variable inside of insert, and then we're trying to use the database anyway. We can't do that. That's exactly what Rust is complaining about. It's saying you're using it after you've moved it. This is use after move, and it's not allowed. Now let's think about what would happen if this were allowed. We said in insert that at the end of this first call to insert, self will be dropped and that memory will be freed. If we were allowed to call insert again, we would try to use that memory. We would use memory that's already been freed. That memory has already been deallocated. It's effectively not there anymore. And what we could potentially find there is just junk on the heap. There would be memory that we should not be reading because it's not actually valid memory. This in C and C++, this is a common bug called use after free. And in Rust, it's not possible. It's not possible to use memory after it's been freed. Any questions about this? Now we got some other error messages here as well. When we look at the error here, we're essentially getting a very similar error. It's saying we are borrowing the moved value key. Now, what does that mean? It's not exactly what we got before, but it's similar. Key is also being moved into insert. Let's take a look why. When it's just uppercase string like this, that means it's being moved. That's what that syntax means. So when we call insert, the key gets moved inside, and this key here has been moved into the insert function, we're not allowed to use it anymore. For the same reason we weren't allowed to use database again, we're not allowed to use key again. And in fact, it complains and it says that we tried to use it again. Now it gave us a little bit of a different error message. It said borrow of moved value. Why is that? Instead of use of moved value? That's because to uppercase here borrows self, and we're gonna look at what borrowing is in just a second. But borrowing is a way of not taking ownership. So to uppercase, the to uppercase function doesn't actually take ownership over key. And in fact, if we go ahead and move this to the line above, you'll notice we still get error messages, but we don't get any error message about key. That's because key, we called to uppercase on it. It borrowed key, it didn't move it. It returns back a string, essentially it created a new string. And we can tell from this function signature right here very clearly that string is a fresh allocation. We went from a borrow to having an owned value here. That means that this string cannot possibly be the same string that self is. They have to be different strings. And so we pass in a new string to the first call insert, the new key to the first call insert that gets moved in. And then we pass in key here. And that's totally fine. So how can we start fixing these error messages? Well, we already saw about borrows, right? Borrows, just like to uppercase here, this ampersand self means don't move self into this to uppercase function, borrow it. And what borrows really are is just like kind of the analogy of books, right? If I have a book and I transfer ownership, in Rust that's a move, and I give you the book, you now have the book, and I'm not allowed to use it anymore, unless of course you give me ownership back. The other thing that I can do is I can still own the book, and I can give you the book as a borrow and say, you can have this for a while, but I'm going to need it back. And that's what borrowing is. Essentially a way to say, you can have this memory for a little bit, but I'm still in charge. I can own it, and I'm ultimately responsible for freeing its memory at the end of the day. There's a question in chat, a really good question in chat. This about, is there a reason I'm using a combination of keyword args and positional args in this first call to insert, which I believe chat is referring to this key colon here. I did not write key colon. That is Rust Analyzer, the IDE experience showing that the first argument is called key, but there are no keyword arguments in Rust. There are only positional arguments in Rust. Just so happens that the Rust Analyzer IDE experience can, I can't edit this at all. Like, I'm trying to highlight it, and like I can't delete it. I can't do anything with it. That's Rust Analyzer inserting in. So there's only positional arguments in Rust, no keyword arguments. Unfortunately, something from Swift that I really enjoy. There's a question, so Rust does call by reference and not call by value. Not really, right? Call by, we are both passing by reference and by value. When we move a value into, right here, we are moving self into insert. That's by value. We're moving it into the insert function. To uppercase here is borrowing self with this ampersand self, and that's by reference. And in fact, that's what that's called in Rust. This ampersand is a reference. You can say reference to self, a reference of self. So if we try, instead of moving self in here, can we do something like this? Well, then it really freaks out, right? And says, must follow the name. Okay, well, let's just delete this real quick. What happens then? So now we don't get this error up here anymore. You notice There's nothing wrong with this up here. We're still getting the error with value. We haven't fixed the error with value, but at least our database now, we can call insert twice in a row, because database insert is now borrowing the database instead of moving ownership into it. But we get another error that we didn't have before down here. And let me go ahead and show cargo check again, because it's a bit clearer when you're not used to it. It says cannot borrow self.map as mutable as it is behind a ampersand reference. And Rust again is being very helpful to us. Again, shout out to the compiler. Read the error messages; they can be very helpful. It says consider changing this to be a mutable reference, ampersand mute self. So what we see here is that ampersand borrows are immutable borrows. We can't mutate values through them. We can simply view the values. Whereas this ampersand mute or ampersand mut or whatever you want to call it value, ampersand mute self here is a mutable reference. We can mutate values through it. So let's heed the Rust compiler's advice here and go ahead and say ampersand mute self. And this compiles fine now. Now we're back to another error with database again. Lots of errors with Rust, right? So now it's saying I can't borrow database as mutable because it's not declared as mutable. So chat was asking before, why didn't we have to write let mute database here? And that's the reason for that is before we were transferring ownership. Before we were not mutating this database variable at all because we transferred the database into insert. Database was like, I don't know what happens after this. I don't own database anymore. I've moved the ownership into insert. I'm not mutating it. But you did notice we did have to say mute self before, right? Before when we were doing the ownership thing, we wrote this. That's because self was being mutated. So it's only the variable that is being mutated that has to be declared as mutable. And this works fine. We've said that insert borrows mutably the database. We've said that database will be mutated in this scope. And so we can call database insert multiple times. If we would remove mute before ampersand self, would it mean we cannot modify self value on the heap? So there's a chat was asking a very interesting question here, like when we remove this, we can't do this anymore because the ampersand self is no longer a mutable reference. We're no longer mutably borrowing. We're immutably borrowing. We can't change a value when we've immutably borrowed it. That's what immutable means. It does not mutate. Now, something that chat mentioned that should be addressed as well, that's not quite correct. Chat was asking, does this mean we can no longer mutate map on the heap? And again, if you're not familiar with heap and stack, don't worry too much. You'll become more and more familiar with it as you write Rust code. But for those that are comfortable with the idea of stack and heap, map here is not on the heap. When we create a database here, this hash map is all stack allocated. The string data. The actual data of this string is, and the hash map data as well might be heap allocated, but our database here is sitting here on the stack. And so when we borrow self here, essentially what we end up with is a pointer to somewhere on the stack. Now, if that doesn't make any sense to you, if you're like, I don't understand any word he just said, don't worry too much about it. This is a concept that becomes more familiar the more you use Rust. There's another person in chat who is mentioning C++ stood move. So if you come from a C++ background, I can explain this to you in very short terms. C++ has copy semantics by default, and you use stood move to opt into move semantics. Rust has move semantics by default, and you can opt into copy semantics. Again, if you're not from C++, that's gibberish to you. Don't worry too much about it. Surprisingly enough, you will understand what that means, and probably after this video. Okay, so I'm gonna put this here, ampersand mute that we had before. That's good to go. So we only have one error left here, and that's this value here. And it's the same thing that we did, use of moved value. Ironically named value. It's a bit confusing, right? Use of moved value, named value. That's what you can always read these ticks as meaning. It's meaning some kind of type or variable name or something like that. And this is the exact same error that we were getting before with database when we were taking database by value. We are also taking this value. We are moving this value string into insert. And so now the question, unlike when we had just self here before, we knew that self would be freed at line 33. Value does not get freed on line 33 because, again, we have those two questions we have to ask ourselves. Does value get moved? And if it doesn't, where does it go out of scope? Well, the answer to the first question of does value get moved again is yes, it gets moved into this call to map insert right here. So value will be moved into the map. And, the map is not being dropped until our database is dropped. So essentially, we're moving value into the map, and then our value string here will not be dropped until the hash map itself is dropped. All right. So we're moving value into database.insert here. And then we try to use it again. We try to move it again into database.insert, but we've already moved the value. We've given over ownership to the first call to insert. So we can't, we don't have ownership anymore. We can't use it again. So how can we get around this fact? Well, the easiest thing is to not give ownership to the first call of insert, right? Now we could try something like, okay, what if we tried to do ampersand value? This turns value from moving value into the insert call to borrowing it. And we're going to get an error message here saying, hey, I expected you to give me an own string, but you're passing me an ampersand string instead. You're trying to pass me a borrowed string, but I need ownership of this string because I'm going to move that string into the database hash map into here. So that doesn't work. Well, what else can we do? The thing that we're going to do here is going to be your best friend for a lot of Rust programming, and especially when you're getting started and you're not fully grasping with the ownership system. You can use this tool to kind of get out of jail free, in a sense. Don't let people convince you that using this is a crutch and the wrong thing to do. Rust allows you to be very, very efficient, but for some things, it doesn't matter. You don't need to be that efficient. Rust is already fast, even if you're being quote-unquote careless. So you can use this tool, and the tool is .clone. Now, what does clone do? Clone, as we can see right here, takes self by reference. It borrows self and returns, this is a special type here, uppercase self, which means the type that implements this function. So in our case, we're calling clone on string, so self here will be string. So what it does is it borrows the string and returns back a new string. turns back an owned string, which is exactly what we want. Now think about that for a second. We're borrowing the string, but we get back a new owned string. What that means is that there's no way that the string that we borrowed is the string that we're getting back from clone. And the name clone should be a hint to that. Clone is really cloning the value. It is allocating a new string with the same data that value has. So here we are creating a clone of value and passing ownership of that clone into the first call to insert. And so value has only been borrowed up to this point. It was borrowed by clone, the borrow is over, and we can pass value into insert now by ownership. Now, if we tried to use value again, like let's say we want to print out the value was, we'll get an error again because we've moved value into insert and we can't use value anymore. See, we're trying to, in this case, borrow, because that's what println does. It borrows everything that it uses. We're trying to borrow the value, which has been moved. Any questions about this? This is the absolute foundation for Rust ownership and borrowing semantics. If you can understand this, then you are 99% of the way there. It's really just kind of applying these core concepts, to more complicated situations. So there's a quick question about std copy, which chat is referring to probably to there. So there is no std copy. Is it std swap that you mean, or std replace, perhaps? Let me know which one you're referring to exactly. We could talk about that, although that is a little bit of it's referencing a advanced beginner video that I've done before, so it's not something that you're expected to know for this, but we can talk about it still. Any other questions about this? About movements, moving into functions and then trying to use them or borrow them afterwards? Okay, go ahead and look and see if you find out what it is, and I'm happy to answer the question. Now, maybe a question you're asking yourself when you're writing code is, okay, if I create a method, like, how do I know? How do I know whether to take the value by ownership with just self, or to borrow it immutably with ampersand self, or borrowing it mutably with ampersand mut? And the answer is that you at first should try each one and use the one that works, is the kind of cheeky answer to that. But you should try in a specific order, and that order is immutable borrow first, mutable borrow second, and then self by ownership third. And the reason for that is that each one is kind of more demanding than the previous one. When we take self by ownership here, we are claiming ownership and saying, the only way you can call me is if you own this value. If you've borrowed it, you can't call this method. It won't compile. And I'm going to either destroy this value or move ownership somewhere else. So like I'm in charge of its fate now. And that's pretty heavy-handed. Whereas when you have an ampersand self here, all it says is like you don't have to own the value, you just have to have a borrow of it. Somebody handed you a borrow of this value and you can still call this method. And that's quite useful. And then ampersand mut is kind of in between. So chat is asking about stdmem replace real quick. We talked about stdmem replace in another video, so if you haven't seen it before, don't worry too much about it. We're gonna look at it again real quick because I think that it's interesting to look at its signature. Let's see here. So this is a generic function. We haven't seen generics too much so far, but just know that this function works on any type t. So you can just replace t here with any type you want, as long as t is the same type in every place. So just imagine instead of t here, we had string. So string, string, string. And this is a very interesting, this is a very interesting function declaration. What stdmem replace does is it says it moves this source variable into destination and returns back the previous destination value. And there's a couple of things we can glean from this from what we knew before, right? stdmem replace requires that we pass in ownership of this source value. Whatever source value that we have to own it. That's because this replace value will take it and kind of place it wherever this destination is pointing towards. And then it takes the thing that destination was pointing for and gives you back ownership of it. Now, this won't help us in this case, right? We have value. We have nothing to replace it with. We can't really use stdmem replace here to kind of accomplish what we want. We simply don't want to move value into insert. We want to we need another string that we can move into it, because insert requires ownership of the value argument. And so the only way to give that to it is by either passing value in with ownership and then we can never use it again, or by cloning it. And chat is saying, someone with a little bit of experience already in Rust, using clone all over the place. And clone is not something to be ashamed of. Clone is something to use when you need to use it. Sometimes there are ways to get around needing to clone, and that's great. And as you learn Rust more, you can start using those things to create algorithms and functions that don't really clone any memory, that are super efficient. But for our database here, we don't need to be that efficient, and there are a lot of programming languages that do things like clone automatically for you. If you use a garbage collected language, if you create a new variable, it's probably going to, it could end up cloning that. And in fact, C++, a systems level like C++, even assigning something to a variable will end up cloning it. So Rust is trying to be extra cautious with efficiency here and saying, I just need you to be sure that you're okay with cloning memory. And a lot of the times the answer is, yeah, I'm okay with that. And chat saying that they're feeling a lot better about their clones and two owns. Yeah, don't worry too much about it. Now, if you're writing like a zero copy, deserialization library or something, and you don't want to copy data, that's part of what you're trying to do, then clones are, you can't clone because you're trying to not clone. But for a database thing like this, come on, clone. It's fine. Okay. The print, there's another question. What about the print line macro here? Is it not taking ownership? No, print line, and because it's a macro, it's a little bit harder to see because you can't actually see the arguments that it takes, which is a bit unfortunate, but print line always borrows its value. The reason is it doesn't need ownership of it. It just needs to read from the value to know. And it will, key is a string here. It's going to copy the data from key into this string buffer that will be printed out to to standard out. I mean, print line itself is already very expensive comparatively, and so like if you're printing something, copying some memory is not a big deal. If you want to write a super well-tuned print function or whatever, then you can take values by ownership and move them into the buffer that will ultimately be sent to the operating system to be printed out to the screen. But that's overkill. All right, so we've gone ahead and inserted our values here. Now what do we want to do? Well, we insert the values into our map in memory, but we're not actually writing them to disk anymore, right? We write them into our in-memory database, and then the program ends, and the memory is freed, and our database is still what it was before, right? So we need some kind of way to write it out to disk. So I'm going to create a flush function here, or flush method here. And it's going to take self, and I'll explain why in just a second, and no arguments. And it's going to return a result of unit. So if it works, we just say it worked, and we don't return anything interesting, just unit. And if it's an error, we return stood IO error. Now, I don't believe I mentioned this last time. There is actually a type alias for result of something and stood IO error, and that is stood IO result. And you can get rid of the error type. So the stood IO result is just like normal result, except the error type is hard-coded to be stood IO error. So we'll use that instead. And inside of here, what we're going to do is actually flush out our database to disk. We're going to create a string buffer with all of the keys and values in the format that we expect, and then we'll write that to disk. All right. So how can we go ahead and do that? Well, first we'll try it this way. We are going to create a string buffer. So we'll call it contents. And we'll create it using string new. So this is just an empty old string, nothing special. And then what we're going to do is we're going to loop over the keys and the values, and we'll call those pairs in our map. So iterating over self.map gives us each key value pair in turn. And when I get to a point like this where like I'm trying to write some code and the compiler is all yelling at me with these red squiggly lines, and I'm just like, you know, I know that I'm not returning a result type at the end of this function. Like, I'll get there. Like, a good thing to do is put to do in. And what to do says, you can even write a message in here, finish this method. To do just like gets the compiler to calm down. If we were to run this code, it would, you know, it compiles, it would run. If we were to reach this code when running it, it would panic. And this is a great way to just be like, I'm working here. Let me finish. Now, it doesn't magically like fix all your code. If you have like other problems, then you have to address those. You'll still get red squigglies, but at least it kind of says like the rest of the function, just pretend that everything, you know, type checks. All right. So we're going to loop over our key value pairs in our map here, and we're going to, we could do what we did before, like where before we called format here, and we said it's going to be key, the tab character, the value, and then a new line. And we got to do pairs. This pairs, by the way, is, as you can see here, is a tuple of string to string, and tuples are simply just kind of like arrays, but you can have different types at each index in the array. We happen to have a tuple here of string and string, but you know, tuples can also support heterogeneous types here. And the way that we actually access the first element in here is with .0. So the first element in our tuple is the key string, and the second element is the value string. So this is giving us for each key value pair the kind of line that we have here. And then we can do contents dot push string like this, and then pass in kv pair like that. Now this won't compile for for reasons that we'll talk about. You may be tempted, for instance, to do something like this from other languages: contents equals contents plus kv pair. And this it will work as long as you borrow this right here, and contents has to be declared mutable. This works. This is totally fine. We could do it like this. I think the more idiomatic approach, though, is using this push string, and it also requires to borrow. So you can see here, push stir here takes an ampersand stir. Now, you might be thinking, okay, kv pair is a string and we borrow it. Why are we allowed to pass in an ampersand string when it expects an ampersand stir? That is not for today. That has to do with automatic dereffing, where on dereferencing we can types can be cast to one another and stuff like that. It sounds way more complicated than it is, but we're not going to get to it today. Just know when you have ampersand stir, you can pass in ampersand string where that's used for now. We'll talk about that more coming up. So now things are looking good, right? Like we've got contents. We're iterating over the map. We're like formatting the line as a string. We're writing that string to contents. Now all we need to do down here is write std fs write and we pass in kv.db here and the contents. And std fs write returns a IO result, and so everything type checks here. Any questions about this? This flush function should work, and in fact, if we go ahead and I think maybe our thing does not handle if we don't have a database already, which we don't. We don't have a kv.db. Let me just, yeah, it panics. So we don't handle the case when we don't have a kv.db. Let me go ahead and just create one real quick. It will be empty. There's nothing inside of it. Can handle that error in just a minute. And we'll run again with our key, called key, and our value called value. Not very inspiring. And if we go ahead and look at our kv.db, it's empty. Why is that? Because we never called flush. And I totally did that on purpose. We got to call database.flush here, and we'll unwrap the error. So if it fails, we'll at least crash the program. All right. Let's run that again. And if we look at kv.db, we have key with value, and we still are doing the uppercase key and value. And if we go ahead and run it with new key and new value, we are still correctly keeping the old values around. So we fixed our bug, which is great. Now you may have noticed down here in Flush that I took self by ownership here. Why is that? Do I have to do that? Would I said before, like, try and do ampersand self first? Wouldn't that work? Well, it doesn't quite work, right? It doesn't quite work because we are trying to take self.map by ownership here, which we can't do because we're borrowing self. So we can't, that's one thing that you can't do when you borrow something. You can't take ownership of pieces of it because you don't have ownership of the whole. And when we call self.map here, we are, the dot syntax tries to take ownership of things. But that's an easy fix. Instead of taking ownership, we just do ampersand self.map, and that borrows self.map instead of trying to take ownership. And this works fine. So, but I still think that taking self by ownership is the right thing to do here. And in fact, this still compiles like this. Why? And this has to do a little bit where you can use the ownership system for API design, which is pretty cool. When I was thinking about the database here, I thought, okay, how are you going to use this? We're going to create a database with new, we're going to insert a bunch of functions, and then we're going to flush it. And I think that a good thing to do is make sure that people don't insert values after they've already flushed it to the database to disk, right? It's probably a good thing. We don't want people to like flush the database and then insert a few more and then not call flush again. Wouldn't it be nice if our database simply required that when we call flush, we could never use it again? So flush is kind of like enforced by the type system as being the last thing that you could possibly do with the database. And that's exactly what taking ownership does. We take ownership of self, and nowhere else can that database ever be used again because we've moved it into flush. And so up here, you know, if we try to do database dot insert string from, and I'll explain string from in just a second. Wow and string from woo. We can't do that because Flush has taken ownership and we can no longer use database anymore. Now this is purely an API design. I have decided as the API owner that Flush should be the last thing that you do with that database, and you can no longer use the database after you call Flush. For this, you can make the argument maybe that's not the best API design. I think it's quite cool, but there are a lot of different use cases where you have certain things where you want, like when you call, have you ever written some code where you say, like, once you call this method, don't do this other thing anymore? Like, once you call this method, like, this other action becomes an illegal thing to do. You can model that in Rust with the ownership system. Simply have that last thing take self by ownership, and now the other actions are no longer available because self has been moved into that method. Does that make sense? It's a little bit of API design early in your Rust career, but you'll start thinking about ownership not only in terms of memory but also in terms of API as well. All right, so this is looking good. Now there's a couple of things that I'd like to clean up, not because they're wrong, but just because they're maybe not the most idiomatic, or even, you know, I've done a big speech about how we don't have to we don't have to care too much about performance here, but I can't help myself. We're going to do a little bit of cleaning up the performance of this thing just for fun. The first thing is here, we call this this pairs here, this tuple here of the key and the value. And then we have this weird .0 and .1 syntax. Like, that's ugly. Like, you know, I guess we could go ahead and say let key equals pairs .0, just so that, you know, we don't have to call it pairs .0, because that's just strange. I don't really like that. This works fine. But another cool thing that we can do is just get rid of this entirely and change pairs into a pattern that we match on, where we deconstruct and say the thing that you're going to get back for loop is a tuple, and the first thing we're going to call key, and the second thing we're going to call value. And this works fine, and I think is much more readable. So the for loop for every iteration gets back a tuple where the first thing we call key and the second thing we call value. Probably easier to read. Now the next thing that comes to mind when I'm looking at this is, okay, when we iterate over each key value pair, we call format, and what format is giving us is this string that we call kv pair. Now, when we want to ask the question of when something will be deallocated, when it will be destroyed, is to ask, okay, does it move somewhere else? If it does, then that new thing that it's been, where the value has been moved into, will be responsible for its memory. But kv pair is not being moved anywhere. We borrow kv pair here, and then we never use it again. So kv pair goes out of scope at the end of the for loop iteration, and that means kv pair will be destroyed on line 41. So for every key value pair, we're creating a string, and then we're borrowing it and then deallocating it. That doesn't sound so. It's not super efficient. Totally correct. This code works fine. It's just not optimally efficient. And I know I said before, don't worry too much about efficiency, but sometimes you want to care about it, and so you should start thinking about, you know, you should understand, do things inefficiently, not because you don't understand why you should do it that way, but because you don't care, right? So when you do care, you can take advantage of that. So what can we do instead to not like allocate this temporary kv pair string, but instead simply go ahead and write these into the contents string itself? Well, what I would probably do is do something like this: contents, not const, contents dot push string, and then pass in the key by reference, and then contents, not push string, but push, and push takes a character, a single character, and that's going to be the tab character. Oops. And then do the same thing where you pass in value here, and then push on the new line character. Now this is a little bit more verbose. We've written 2 more lines of code than we had before, but it is more efficient in the fact that now we are not creating a temporary kv pair string. We are simply taking the values from key and copying them onto the content string directly. Any questions about this? Now this is most likely the code that I would that I could see myself end up writing. Oh, there's a great question in chat about, do we need this ampersand key here? String is key is already an ampersand string, and brilliant. That's great. You are correct. We don't need it, so we can get rid of these. Now, this is a good point about seeing through multiple borrows. So when we did this before, we actually ended up passing into this push string method here is an ampersand string. So a borrow of a borrow. Yes, you can borrow borrows. You can borrow references, a reference to a reference. But that's totally fine. Like, we can totally legal syntax. This compiles just fine. We are just borrowing over and over and over again. And of course, you know, semantically, this makes sense. It's a bit weird. Rust has this thing where it sees through multiple borrows, and if you just need an ampersand whatever, you can pass in a reference to whatever, and that's still fine. And at the end of the day, this compiles down to essentially, you know, essentially nothing. Essentially this. All right. So something is triggering somebody in chat that we have not cleaned up before, and now that we're doing a little bit of refactoring, we can go ahead and clean it up, and that is this database map:map here. And there's a 3 dotted lines put in here by Rust Analyzer because it's also being triggered a little bit here. What we can do is simply, there's a shorthand where we can do this. When the field of a struct and the variable that you want to populate that field with have the same name, you only have to write it once. This is borrowed from JavaScript. It's quite nice. So because database has a map field and we are populating the map field with a variable called map, we only have to write that once. Now, someone in chat is saying that in C, this would be referred to like as a pointer to a pointer to a pointer. References at the end of the day are pointers. They're just a little bit more of a high-level concept, and they're safe pointers. They're pointers that don't. They're pointers that you can't misuse. So, in essence, this isn't really that different from having a pointer to a pointer to a pointer to a pointer to a string. It's roughly the same thing. All right. Any questions about this? We've reached a good spot. Now, this flush thing is interesting. We've already had a bug with it before where we forgot to call flush here, right? Do you remember that? Like we tried to run it and I hadn't written this line yet. And I ran and I looked at the database and it was still empty and I was like, wait, what did I do wrong? Oh, I forgot to call flush. It's a little bit sad, right? That we have to remember to call flush when we're done with inserting into the database. Wouldn't it be nice if, like, once we're done with inserting into the database, like, flush was just called automatically? And it turns out that there is a way to actually do that. And that is by implementing the drop trait. And what drop is a trait, which we haven't talked about traits yet. We're going to get into that. But drop is a way of specifying behavior that will happen when an owned value goes out of scope and is dropped. Now, by default, what happens when when a value goes out of scope is that all the memory is freed, and that is automatic. And even if you implement drop, you're not overriding that. That always happens. But you can add extra functionality that happens when an owned value gets dropped by implementing this trait. Real quick, what traits are, we're not going to really dive into that today. That's something that we're going to do next time. But what traits are is a way of specifying functionality for multiple types in a similar way that interfaces in other languages are, where you can say, here's a function that belongs to this trait. Multiple types can implement this functionality, and then we can use those types wherever we expect a type that implements that trait. what does that look like in syntax? Well, we can do impl just like we did before, but instead of doing impl database like we did before, we do impl the trait, in this case drop, for database. And if we do this, we'll get an error and saying, we look here at the error, like not all trait items are implemented. We're missing the drop function. So we have to implement this function in order to implement the trait. And drop is a function. It takes an ampersand itself here. And this will be called automatically when a value is dropped. And so what we could do here is we could go ahead and just like copy all of this into the drop functionality, right? And then essentially we don't even need flush anymore, right? Because flush is just going to be called automatically, automatically for us on drop. I'm going to keep it for a second. Whoops, my undo stack got a little messed up there. I'm going to keep it for a reason we'll talk about in just a second. That's a very good question. In chat, they're asking, how is drop here in scope? And that's interesting because there's a whole bunch of stuff that's already in scope, right? Like string, how is that in scope? Result, how is that in scope? Like we're using std.io error here with fully qualified. Where is result from? Well, it says here, in this documentation, it's in core : result. Like, why can we just refer to it as a result here? Well, in Rust, there are a handful of types included in the prelude. And in fact, let me go here to docs.rs. And if we go here, you can see this is the prelude, which is a strange term for types and functions and stuff that are automatically imported on your behalf without you having to do anything. So these types here are always in scope no matter where you are. Like clone, the trait clone, we talked about clone as a function. Clone actually comes from a clone trait. It's implemented on a bunch of things. But like string, vec, which we haven't really talked about, option, for instance, sum and none, we talked about option. Here's result. This is why result is able. This is why we can use OK and error, because by default result, and this self here basically means like the result type itself. So the result type itself, its OK variant and its error variant are all included in the prelude. That's how we can refer to it unqualified. And here's drop right here. So we can refer to drop without qualifying it. Anything that's not in this list, we have to refer to it as a fully qualified thing, like stdfs read to string, std.io error, and even hash map up here. We have to at least, we can stop doing that by using this use statement here, and we can do the same thing with stdfs read to string, but we don't get that for free. Hopefully that answers your question. So there's one error that we're getting here in drop, and that's hopefully should be somewhat apparent to you, that we call stdfs write here, and that returns a IO result, right? It returns an IO result because writing to disk might fail. Writing to disk might fail, and what that means here is that, what can we do to get this to compile? We can just say like ignore the result, but then we get a warning. I mean, it's not an error, but we get a warning saying like, no, this result is legit. You should at least acknowledge that it exists. You got to at least acknowledge that it exists. There's a way to acknowledge it existing and still not use it, and that's by doing this let _ equals. And what this syntax says is like, put it into a variable called underscore, and we're just going to ignore it. I don't care about it. This is a great way of acknowledging, like, I know this thing returns a value, in this case a result, but I don't care. So this is fine. But it's a little bit of a shame, right? Like, what if we care whether stood fs right actually fails or not? We have no way of knowing it, right? So that's why I kind of want to keep the flush around. What that means now is that with flush, you can call flush if you want to handle the result, or you can just let it drop. And in fact, what we can go ahead and do is just call self dot. We cannot call self dot flush. We here can call drop. Oh, we can't. Sorry. Huh. We have to. That's unfortunate that we have to copy the contents. I think in order to fix this, we would do something like this. Move it out into a function where essentially all we require is an ampersand database. Now we have a function here that takes a database, so we're no longer using self here. And it's actually going to flush out to and of course what we want to do here is return a stood IO result of unit. Let's not ignore the value down here. So now that we have this standalone function, we can call it in multiple places. We can call flush here with self and just ignore the value. And we can call flush up here with self. And we got to pass in. So now we've reused the standalone function in two places. Now you'll notice here with, and maybe it's a bit confusing that these are like called the same thing. We can call this do, and in fact, let me go ahead and do rename symbol do flush, so that we can differentiate between flush the method and flush the function. All right, you'll notice we are passing in ampersand self here because this requires an ampersand database. Self is a database, but it's an owned database, so we have to borrow it first. We don't have to do that here because if you have an ampersand mute, you can pass in that ampersand mute thing wherever an ampersand thing is required instead. So chat is asking, why can't we call self.flush in drop? That's a very great question that I kind of brushed over because I wasn't expecting it at first. Let's look at the error when we call self.flush here. We get an error. First error, we can ignore the result because we don't care about it. Here's the real error. Cannot move out of self, which is behind a mutable reference. And in fact, this is really great to look at in terms of what cargo check shows us. Oh no, it's not. They don't have they should have a nicer one for this, but still, this is good. Cannot move out of self, which is behind a mutable reference. So self here is ampersand mute self. We are borrowing mutably self right here. Flush needs ownership of self. we don't have ownership of self inside of the drop implementation for very good reasons that we won't necessarily talk about right now. But when drop gets called, it gets called with ampersand self, ampersand mute self, and we can't call flush, the flush method, with ampersand mute self. We have to have ownership. So that's why we don't use self.flush inside of drop, because we can't. It won't actually compile. So let underscore do flush. And this should work. All right. We do have one probably not terrible bug, but I would say it's a bug, in that when we call flush here, we call do flush, which actually flushes it out writes it to disk. And because self here is owned, at the end of this function, self gets dropped, and then this drop implementation gets called. So we're going to end up calling do flush twice. And I mean, just to prove it to you, like print line do flush called. And if we go ahead and run, come on. If we call run here, and we need to, call flush again. If we actually manually call flush, then do flush gets called twice, right? So up here, we're calling flush. Perhaps, we don't want to unwrap here. We wanted to do a little bit of fancy error handling here, where we say if it's okay, then, print line. Come on, Ryan, you can type print line. Yay! This is our fancy error handling here. And if we get an error, then we can say like, oh no's, error. And we couldn't do this. If we were just using the drop implementation. We have to call flush because flush actually gives us this IO result here. Whereas that's just ignored in the drop implementation, because this gets called not by us, but by kind of the compiler inserts calls to drop for us when values are dropped. And so it would be really cool, and this is the last thing that we're going to be doing for today. It would be really cool if we could go ahead and keep track of whether flush was called. And if flush was called, then not run flush on drop again. And this is pretty easy to do, right? We can just come up here and say flush is a bool. And we can say flush here is false. And if flush gets called, we say self.flush equals true. And this won't compile because self is declared as immutable, so we have to mark it as mutable. And then in drop, we simply just have to say if self.flush, if it's not flush, then run. And now if we run it again, flush is only called once. So that's pretty straightforward. There was a question about whether in Rust if you can take functions as arguments, and you can. We're not going to get to that today, but you can take functions and arguments, and there are also closures in Rust. So functions that can capture values from their environment, and that also exists in Rust and is quite useful, and we won't get to that today either, unfortunately. Now there's something interesting here. Like we decided in our API for Flush here to take ownership of self. That's totally legit. This is fine. If you think this is a good API design, we're done. But maybe we change our mind. Maybe instead we think like, I really wish that you could call Flush as many times as possible. We could do this instead, and this also works fine. And now we should be able to call, Flush, and then we can call database.insert with, new keys and new values, and that will work just fine as well. Could we also do this? The answer to this is no, we couldn't, because we are writing to self.flush. We are mutating self when we are only borrowing it immutably. So as a little shout out to next time, what we're going to be talking about, since we're at the end of our hour. Next time we're going to be talking about what the actual difference between ampersand self, like borrowing self immutably, and ampersand mute self actually is. Is there any actual difference between it? It turns out there is. Turns out that ampersand self is a lot more flexible in how and when you can use it, and ampersand mute self comes with a big old asterisk next to it, making it less flexible. And we'll kind of wrestle with the idea of ampersand self and ampersand mute self, borrowing immutably, borrowing immutably, when you can do one versus the other, what the consequences of doing one versus the other, and we'll talk about ways to bend the rules and start overcoming these limitations in various ways. So with that, I think we're going to call it a day for today. I want to answer any last questions, any questions about what the code that we did for today, or any questions about Rust in general or about this tutorial in general. I'd be happy to answer. But if there are no other questions, then make sure, please, you can find my information at the very top of the screen. GitHub, Twitter, and YouTube. Please feel free to subscribe to anything on there. Twitter is where I announce my streams. YouTube is where I post them after they're done. And of course, Twitch, if you're watching live, is where I actually live stream. Please follow me there as well. I hate to ask every time for follows, but it does provide the necessary proof to myself that people are actually enjoying and finding value in this. So it really does help if you go ahead and do those things to follow me on these various platforms. It means a lot. And thank you very much for your attention. There will be a next stream, as we just talked about what will be in the stream. When it will be, I don't know yet. I'm going to try and do it next Friday, but no promises. Is there a debugger? Yes, Rust produces kind of normal executables with normal debug info. I'm going to get this to compile again. And hopefully I have everything set up in this environment, but here in VS Code, for instance, you can set a breakpoint and then hit debug here, and then it will launch and do strange things. I don't know why it did. We need to first set a breakpoint here. It panicked, which is why we never hit our breakpoint. We hit the panic handler there. Go ahead and do that before we panic, And you can see in here that we're fine. The debug experience in Rust is not super amazing. It's not as good as in some other languages. That's not really a bummer though, just because you end up debugging a whole lot less in Rust. I almost never use a debugger unless I'm writing unsafe Rust, which is the superset of Rust for doing nasty, horrible things like using raw pointers and stuff like that, which you only very rarely need, depending on what you're doing. Sometimes you may not ever need it. That's when I use a debugger. Otherwise, throwing in a few print statements in the off chance that I have a bug is usually faster than running a debugger. But yes, there is debugger support. You just hopefully this gets better in the future, but for now it's not that amazing. And then there's a question of, do you find you can be as productive in Rust as in higher level languages like Go or similar? Yes and no. It depends on the it kind of depends on what you mean by productivity. First of all, a lot of people define productivity simply as like, can I write a ton of code? Doesn't matter if that code works, doesn't matter if that code is maintainable. It just like, can I type as much code as possible in an hour? And if that is your definition of productivity, then Rust is not super productive. You could still write a lot of code, especially once you get familiar with borrowing and ownership and stuff like that. But there are languages out there that are much more productive when it comes to just like raw output of like getting stuff written. That's a bad definition of productivity in my estimation. I think productivity should be defined by, can you produce correct code that is maintainable and will continue to work in the future? For some use cases, that doesn't matter. If you're prototyping something, it doesn't matter if you're writing, code that's maintainable. You're going to throw it away anyway. But at the end of the day, Rust is really great at creating maintainable code early on. It is less good for prototyping throwaway stuff than some other languages. Although it's not as bad as a lot of people think it is. So that's kind of a happy go around of like, I think Rust is very productive. It's just a definition of productivity that is more holistic and brings in like a longer scope of time than like, can I write a ton of code in an afternoon? Yeah, and someone is mentioning the code Lldb extension. Yeah, if you want to do some serious debugging, I don't think I necessarily have that set up here, which is why I wasn't getting locals in my debugging experience. Lldb is the Llvm debugger, and that works pretty well with Rust. There's some issues with name demangling and stuff where Lldb doesn't know about Rust's naming conventions sometimes, and it doesn't know about standard types like vector and stuff like that. So you see kind of the raw output of what a vector is, with or a string, its data pointer and its capacity and length, whereas you'd really rather just see the string data itself. So it's like not perfect, but if you need to do some debugging, then code Lldb is the extension for you in VS Code. All right. In PHP, you only program the happy path. Ha ha ha. Yes, that's true. Rust is definitely not a language where you can only code the happy path. You at least have to admit that something might fail. Why can doFlush access private variables in the database struct? So here we are accessing .map, and .map here is indeed it is indeed private to database. Privacy in Rust does not work how it works in other languages. privacy in Rust, when we say this is private, it means it's only viewable in the current module. So we are in a module here. We've not really talked about modules. We've only been using one file, but we are in a module here. And so everything that is private to this module. It's this file, essentially. And it is private and therefore viewable to the children modules. So if we have children modules of this module here, then we can also view that information as well. And so privacy is not relegated to privacy of the type itself, but to the module. So if we want to hide, like if we have another module, we would not be able to use database.map. We would have to access that information through public or publicly available means. We'll talk about modules as well at some point. Great. Seems that there are no other questions. Thank you very much, and hope to see y'all around and on the internet. So everybody have a good weekend, and talk to you soon. Bye-bye.